let me present my work in the Galaxy Workshop. And the work that I'm going to talk about today was mainly performed by this amazing undergrad student in Mexico City. And this is the main question that I would like to address today. So are these two observables consistent between each other? On the left side, we have the evolution of the galaxy stellar mass function. And on the right side, we have the evolution of the relation between the star formation rates of the galaxies and the stellar mass. If for a moment we ignore mergers, we will think that if galaxies are growing in time with these correlations, the galaxy stellar mass function should evolve to the left in this panel. So basically, at a constant number density, the galaxy mass function should evolve like this. So, and we have different ways to study this, and I would like to summarize using this slide. And the question that I would like to address is whether these two observables, as we measured, because we obtained from different samples, from different ways to measure stellar mass and star formation rates, the question that I would like to address is that using these two observables only, we can constrain we can see if both are consistent between each other. So the ways that we can address this question is we have a general goal, understand galaxy formation. In this case, I would like to address how galaxies assemble their mass and the number densities and the star formation rates. So we can think it in several ways. So we have the model-based approach, which we can use structure formation models like the lambda CDM, apply hadron simulations, or using semi-analytic models. That will be the model-based way to approach to this question. We have also the semi-empirical galaxy-halo connection, in which we try to combine the model-based, using basically structure formation models, lambda CDM, simulations like the Bolshoi, for example, and combined with the observations would be like the stellar mass functions and the star formation rates. But we have a third way to do that, like the pure empirical modeling, that using the galaxy demographics, like only the correlations between the star formation rates and the mass functions, we can infer the growth of the galaxies, but also using the fossil record based on the spectrum of the galaxies. In the regards of the galaxy-halo connection, which is mainly the topics that I've been working on in the last years, we have somehow addressed this question by combining the halo demographics, basically the halo mass function and the growth of the dark matter halos, combined with the evolution of the galaxy stellar mass function, the star formation rates, and the cosmic star formation rate. So basically, we managed to fit all these observables together with the demographics of halos, and then you will say, well, so why question again, if you are having a good consistency here, why you would like to address this question again if you did it here? But there are several questions. So as an output, you get a correlation between the stellar mass and the halo mass. The halo mass basically is working in this scenario like a clock for the growth of the galaxies. But then the problem is that you can derive only average correlations between galaxies and dark matter halos, and you don't know much about whether the galaxies start forming or quench galaxy. But you can try to generalize that, like for example, Peter Beruzzi will talk tomorrow about that, how to get different populations. But this becomes more complex. You need to introduce another observables like two-point correlation functions, weak lensing, and so on. So this becomes more complex, and you don't know whether you are having good fittings to some observables to others. So, and it is not clear how to generalize this to different populations. We can do it more empirically as using the archaeological approach. We have this paper now in the archive in which we use the manga data using the spatially resolved spectrum of the galaxies in the manga sample using the stellar population synthesis model. And we have recovered the star formation histories of the galaxies for this sample. And we have applied some volume corrections, and we have shown that the data that we derive from the spectrum and the manga recovers the star formation history of the galaxies. But here we are assuming that all the galaxies are evolving only just by star formation, okay? And we cannot constrain whether parts like in the merger, which contribution comes from merger and which contribution comes from star formation in situ. There's this third approach, which is the demographic approach, in which you have fittings to the correlation between the star formation rate and the stellar mass. Using these fittings, assuming that galaxies are evolving around the mean correlation, you can then infer the growth of the galaxies using this mean correlation, which I call the average star formation rate approach. So you can then, using the mean correlations, infer how the galaxies are growing with time, the star formation histories of the galaxies. This is a very recent paper by Schiesler, but also applied previously by Leitner, no? And then, but the previous approach don't say anything about how the whole population is growing based on the galaxy stellar mass function. If we would like to add the information from the galaxy stellar mass function, we will then assume that the population has some initial distribution based on the galaxy stellar mass function, use the correlation between the star formation rate and the stellar mass, and then infer how much the galaxies grow using this star formation rate. So this has been applied previously by Leha 2015, and what he got is that look at the two redshifts that I show here. So he starts with an initial distribution of galaxies at redshift 2.25. And then he used the star formation rates at that redshift and grew the galaxies up to redshift 2. And the result was this. This is the stellar mass function. And the result was that he inferred this stellar mass function, and this was the original. So he had an overproduced number of galaxies. So why this inconsistency, no? Just using these two observables, why we have this inconsistency? He said, well, we can alleviate this tension just by claiming that the correlation between the star formation rate between the stellar mass is a double power law, which I don't think that it's seen with this broken law that Leha is claiming. We don't see that in the data. Most of the time we see power laws for the star formation rate main sequence galaxies. So there's another claiming that, for example, Steinhardt said, well, this steepening of the stellar mass function is not because we require double power law of star formation rate correlations, but mergers. If we assume that all these galaxies are merging, we will obviously lose these galaxies, and they will merge with bigger galaxies. But the survival probability is basically that none of the galaxies are surviving, no? Even for star forming or quench galaxies, which I don't think that makes sense, because when we applied more motivated models based on the structure formation where the mergers, you can count the mergers directly, I don't think that there is so much support. For example, the work that we did using subhalo abundance matching, you don't see that there is a lot of mergers happening, that the fraction that was formed in situ is not that big, and which is more or less consistent with other works based on hadron simulations had been found. So why is it difficult then to reconcile these correlations between the star formation rate and the stellar mass with the galaxy stellar mass functions? One of the questions is, we are always assuming that the galaxies, we have average correlations, that the galaxies are evolving around these average relations. Is this true? Are they just moving around the scatter, or they have like preferential zones? Like, for example, if galaxies are above in the star formation rate, at later times you always find them above, or they are below. That's I think that's part of the questions and why we are finding these problems. So what if we have somehow, using, for example, the Sloan data, here I'm showing the star formation rate versus the stellar mass, how if we infer the star formation histories of the galaxies individually, and having this volume, we complete it by volume corrections, and then we infer how the galaxies evolve using somehow constrain the star formation histories, evolve these galaxies, and try to see how the mass function from this initial condition evolve, and how the correlation between the star formation rates evolve. So this is what I will try to convince you that it's very simple to do this using a very simple approach. And like, let's assume that we know, let's assume that we have a formula for the star formation histories of the galaxies that can be expressed in this way. So basically, we have two parameters, which has some parameter in time, some amplitude for the star formation history. Then we can calculate the stellar mass from this star formation history, in which this number, which will be constant, we can take out from the integral once we calculate the stellar mass. And when we divide these two numbers, which is basically the specific star formation rate, and evaluate it at the observable time, we can eliminate one of the variables. So basically, if we write the star formation histories using this kind of laws, we will get that the specific star formation rate evaluated at some time, it will depend only in one parameter, which is basically solving one equation. So we have examples of this kind of laws, like, for example, exponential laws, tau models, Sandage models, and all these type of models we can solve that equation. So basically what I'm saying is that if we know the star formation rate of the galaxy and the stellar mass, we can find the parameters A and tau. So then we can constrain all the history of the galaxies, regardless where we infer the star formation rates of the galaxies. Okay. In this work, we use tau delayed models in which you have an initial time where the galaxy born. So basically, we fixed that time to 0.75 gigayears. Here, I'm showing that tau models are nice because we have a different variety of star formation histories. Like, for example, here I'm showing for a star-forming galaxies, and here I'm showing for a quench galaxy. So we applied that methodology, which is just basically using this plane. We obtained the star formation history for all the galaxies and the sloan. Here is the parameter distribution that we got from the model. This is the birth time of the galaxies. Most of the galaxies, which was our initial birth time, have 0.75 gigayears. But also we find very young galaxies, like that they born yesterday, basically. This is the distribution of the tau parameters, which is basically the width of the tau delayed model. And this basically is proportional to the peak of the star formation history of the galaxy. So, for example, most of the most massive galaxies have a peak of a peak on the star formation history around 100 to 1,000 solar masses per year. It's just that. Oh yeah, but then if you fit the tau model from the specific star formation rate, you get the tau model, right? But then from the stellar mass evaluated at the observable time, you can get the amplitudes. So you got the two numbers. Oh yeah, right. Okay, I see. The question is how we constrain the initial. Yeah, right. So we found the close. Not all the galaxies you can solve for TI, assuming 0.75 gigayears, but we move to the next TI that we can solve the equation consistently. Right. Okay. So this basically summarizes all our results. So you can see here how is our mass function based on the tau models evolving compared to a compilation that we did in 2017. Here you can see the cloud of all the star formation rates of our model, and the comparison with the medians in our compilation from the 2017. So despite that it's a very simple approach and a very simple model, it's not doing that bad, no? It's very consistent between these two observables. So then we have also computed the cosmic star formation rate, which is the solid line here. We are consistent with previous inferences from, for example, the Madao compilation, and also the cosmic stellar mass density. This is the correlation, just to show the correlation between age and the stellar mass in our model, which is we are comparing with Galaxy to 2005, and also is very consistent with this inference. Here are some average star formation histories for our galaxies, which are shown with the yellow-orange solid lines for different stellar masses. And the interesting thing is that this is the result of several tau delayed models. It's a combination of all of them, quench and star-forming galaxies. And we tried to fit to a tau model the average star formation histories, and we couldn't. The fits are really bad when you try to apply a tau model for the average star formation history. Yeah, so this is the average star formation history for this stellar mass beam, for example. And this is, here we are putting all the star formation histories of our galaxies that they have a tau model. And this is the average, the orange solid line. But when you try to fit a tau model, it's not a good model for the average star formation history. And so then one of the questions is why the previous models failed, no? So basically here we are taking into account that there is some scatter, that galaxies are not evolving around the median relations. And we say, well, we have now a laboratory to understand what went wrong with these models. So here, what I'm showing in the dashed lines is the evolution of our galaxy stellar mass function from the tau models. Sorry if they are to think. And then we fit the mean relations, our mean inferred relations from the tau models using the star formation rate stellar mass. And then we start at redshift 5 and evolve the galaxy stellar mass function using the mean relation, assuming that now in our model the galaxies are evolving around the mean relations. And we observe, again, this overproduce of number density in the galaxies. So that's, when you try to infer using median relations, and you assume that galaxies are evolving on median relations, be careful, because then you will start to think that there are some problems between perhaps the observables, or you will invoke some different mechanisms, but then that is wrong. It was just the assumption. And perhaps this is a very ideal model, but it's showing that we should be very careful when we make some claimings. No? And here I'm just replacing the figure that I showed previously from Liga. And here we are assuming that all the galaxies are evolving just by pure star formation, and we are not invoking mergers. Just to show that we can, because we know how the galaxies are evolving around the about the specific star formation rate versus stellar mass, we can also divide the galaxies between star forming and quench galaxies. We can see how the two clouds are, how the quench cloud is emerging to low redshifts. So we can compare with observations about the quench fractions. I will skip this. I would just like to show this figure where we compute the fraction of quench galaxies as a function of redshift. Here is as a function of the stellar mass, the French fraction. We are comparing with different observations. Our model are the solid lines with the shaded areas. And what we see is that our model is doing a bad job in reproducing the quench fraction. But we expect that because we didn't include mergers. So then we include a model for merging. And as expected, now the model that includes mergers is with the red solid line. And as expected, we increase the quench fraction of galaxies. But then the question is why we are not still doing a good job. Well, it's probably that we need some extra quenching time for our model in order to take into account the correct fraction of quench galaxies. And thanks.
So to follow up on Peter's question, I'm still a bit confused about what you did with this T initial parameter? Because you set it to 0.75, but then you showed the distribution. Some SFHs were allowed to deviate from that.
Right.
Now, I looked at these SFHs in Illustrious a while back, and I just found that these models where you fix T initial just fit really badly. So I'm sort of confused by that.
Yeah, so you're referring to this figure, basically. So we initially started that all the galaxies, regardless of the star formation rate or the stellar mass, all the galaxies start with an initial time of 0.75. But for some galaxies, we can find solutions for the tau parameter. So you cannot feed at the same time the specific star formation rate and the tau parameter. So then what we did is to find the closest, or we move around. Let me put it in this way: we move around this axis, and we found the closest solution where we can fit at the same time the tau model and the star formation rate. So we were just moving like here, and we find that, for example, we start with 0.75, we move here, and if we found that some galaxies have 2 gigayears instead of 0.75, and we solve the equation, and we find a solution for the tau parameter, then we stop. But that doesn't mean that is the real initial time for the galaxy. We need something else to actually constrain that parameter, that perhaps using the other observables.
Yeah, maybe we should talk offline. It just seems to me that you're really, by doing that, then pulling your tau, the fits in a weird direction. You know, like you're probably influencing the tau and A in ways that may not be physical. But anyway.
Sandy?
This is interesting. I'm trying to figure out whether you want us to actually believe the numbers you come up with, or whether or not the significance of this is you use the word laboratory, in which you can make a bunch of assumptions. And is it really?
Yeah, this is more like a laboratory than something real. We came up with an interesting, but one thing that it was surprised is that thing. So that's why we are managing this like more like a laboratory that start to believe that galaxies.
In that spirit, you raised the question, what does a point do that is above the main sequence today? Is it always above the main sequence, or what do you find?
Oh yeah, most of these galaxies, if a galaxy is above the main sequence, they are most of the time above. But the star formation rate has like an attractor feature. Like even if you are below, the galaxies will approach to the mean relation at very large times.
Okay, let's move on. Our next speaker is Francesco Belfiore.